the opponent challenge the reporter for problem, please.
You would like to challenge the problem.
We would like to accept the challenge.
Please write on the all fighters name on the record.
presenting topic 11, pumping straw. So this is a problem statement. A simple water pump can be made using a straw shaped into a triangle and cut open at the vertices. When such a triangle is partially immersed in water with one of its vertices and rotated around its vertical axis, water may flow up through the straw. Investigate how the geometry and other relevant parameters affect the pumping speed. And our main focus is that what are the relevant parameters that impact the pumping speed, and to what extent does the distance vary depending on the various ranges, and how much the water fills in the area of the straw. In our problem statement, we define pumping speed as how much volume of water exits the water pump in a second. So this, and our initial assumptions are that the friction between the water and the straw surface is negligible, and the total volume of water sprayed out is the mass. We will, for convenience purposes, and the size of water droplet is proportional to the volume of water filled in the straw when not observable through other means. So this is a video of our demonstration. We use a drilling press to get a stable water pump rotating, and this is another setup of our experiment. We use the voltage supplier to rotate the axis of the water pump, and we will explain more in depth in our further presentation. So this is our theoretical model. We have the variables, the force exerted on the water expelled from the straw pump, and this displacement of the water in the pump. And T equals to the height of the pump is placed at, and FC is the centrifugal force exerted on the water. And radius, and the large radius is the radius of the pumping spinning pump, and the small r is the radius of the straw itself. So this is our free body diagram in the inertial frame. So we assume the real forces that are exerted in the water is the gravity and the frictional force and the normal force. But in our initial assumptions, we assume the friction force is negligible. So according to our model, we get the equation that the force exerted on this direction equals to mv squared over r cosine theta minus mg sine theta. Then how about the non-inertial frame? In the non-inertial frame, which is the rotational frame, we assume the real forces that are exerted in water are the normal force, the frictional force, the gravitational force, and the centrifugal force. And according to this model, the max, and we tilted the coordinate system into this direction, and max equals to mv squared over r cosine theta minus mg sine theta. From our model, we now know that both frames produce the same result, but if we use a non-inertial frame, it is easier to derive this equation. So this is our simplification of the models. From the distance, we can get the initial velocity of the exit of the water pump in our demonstration. And using our work force model, we get the equation that the velocity squared equals to the length of the straw multiplied by the angular speed squared cosine theta squared minus 2g sine theta at L. So this is the theoretical velocity of the volume of water, and it is when there's different angles of the straws. So from here, we know that when the straw, the angle increases, the velocity of the water decreases accordingly. This is our experimentation. And for our experimentation, we used the number set on the right to observe the impacts of our experiments. So our experimental setup for the low, middle, and high revolutions, which is 2 revolutions per second, and 4 revolutions per second, and 6 revolutions per second, we use the drill press experimental setup below, and we control the time over here. But for very small adjustments, we use the new setup of the motor-based setup we demonstrated in our previous slides, and we recorded the mass of the water and the distance sprayed out into intervals of 10 to 15 seconds, and we did 3 trials for each data point and submerged it along 0.5 centimeters of the straw height. And the distance of the water sprayed was here below. The faster the motor rotated, the further the water was shooted out. And this fits into our initial predictions. And the standard error bars all overlap with the respective points of different diameters of the straw here. So from this, we know that the diameter of the straw does not really impact the pumping speed and the distance. How about the mass of the water sprayed versus the revolutions per second? For the thin diameter straw, we can clearly see that when the voltage of the motor is adjusted to 0.9 voltage, it shows a very big peak here. And the standard error for the 18mm straws were bigger than the other straws, which was an observation we found. Over here, the standard error bars are clearly bigger than other respective points. And we tried to investigate what is going on in the small fine-tuning adjustments of the 0.9 voltage. Over here, the middle revolutions show greater discrepancy between various diameters, and we thought that this is primarily due to the difference in the degree that the water goes into the straw, and this leads to a faster velocity in the thinner straws. And we also thought of another factor that contributes to this phenomenon. For a 2.5mm straw, it further pushes out the water due to capillary action. So over here, we use the equation here below, and we see that when the straw is thinner, the initial water, the capillary action force, it shoots the water, and the water that exits the straw, it starts at a higher height. So from this, it makes it easier for the thinner straws to shoot out the water with greater velocity and with more mass. And this is a decrease in the volume of water. And using a high-speed camera here, we observed that the volume of water in the pump decreases gradually. So when it initially goes up here, it fills in the water completely. However, it forms a little dent here, and then at the final exit stage, the water that exits the stage, it decreases gradually. So it draws like this shape. And we assume that this is due to capillary action, and it doesn't have straight pumping. It requires a smaller force to squirt out the water, as it is already filled in high, so more water gets to exit the straw. Then what about the impact of Bernoulli's equation? The pressure difference between the outside and the inside of the water makes the water pump out from the straw. However, from our derivation of the equation that takes Bernoulli's principle into impact, we observe that this Bernoulli's equation is negligible when we plug in the numbers. So this is a factor that contributes to the impact of Bernoulli's equation. And when we plug in all the numbers, we observe that the density of the air over density of the water, this discrepancy between the two numbers, it makes the factor that contributes to Bernoulli's equation very negligible. So we assume that Bernoulli's equation does not have a great impact in the force the water molecule gets. And we also investigated the impact of buoyancy. Using the high-speed camera, we captured, we did the rotational experiments for 5mm and 18mm, and we did the same for 18mm and 5mm over here. And when it was low revolution speed, only one side of the straw of the pump pumped out water. However, when it was submerged to a more greater degree, it did not. The water pump started to pump out on both sides, but did not really change the cross-sectional area of the shooting water for the two sides. So what is the reason behind this? We assumed that this was the impact of buoyancy, and we investigated the relative impacts between the buoyancy and the drag force. Because when it is further submerged in the water, there will be more buoyant force that pushes the water outwards. However, but if we do that, that would cause more of the surface of the water pump to be submerged in the water, and that causes more drag force. So then, what is the optimal distance to submerge in the water? Submerge the pump into the water. We use the parameters here below again, as we mentioned in the previous slides, to investigate the relative impacts of the two forces. So this is the graph we attained. The mass that the water sprays out peaks when it is submerged by 2 centimeters over here, and then it decreases afterwards. So from this, we can infer that the faster it goes, the more buoyant force it impacts the speed due to gyroscopic inertia. But over here, we clearly see that when it's submerged by 2 centimeters, it has more. It is the optimal speed, optimal depth. Now we also consider the geometry of the straw. Over here, we use the imbalance straw, which has 75 degrees for one side and 50 degrees for the other side. And the force was different for two outlets, and the force vectors canceled out the balance ones. So So the more drag experienced in the 50-degree was due to a larger surface area and does not rotate with perfect balance. And so we initially hypothesized that it will sputter less water and the initial velocity that squirts out will be slower. So this is our experimentation. For the distance of the water sprayed for imbalanced and balanced straws in various revolutions, it showed that the imbalanced straws fall in the in-between range of the 50 degrees balanced straw and the 75 degrees balanced straw. And also that applied the same for the mass of the water sprayed in various angles. When it was speeded up in four revolutions per second, the imbalanced straws fell into the middle degree of the 50 degree and the 75 degree revolution, 75 degree balanced straws. And from this we can know that the imbalanced straw yields the mean result of the balanced straw of the angles on the two sides. This is our conclusion. The general trend was that the thin straw sprays out the most water due to capillary action and non-uniform sputter, and the fact that it sputters water on both sides compared to the thicker ones. And buoyant force plays a part in the speed, and it has a greater impact when the rotation is faster. And the imbalanced straws with two different angles on the end show that the geometry of the straw does not have a great impact in optimizing the mass of the water sprayed out, and the Bernoulli's principle is negligible in this context. Thank you.
Thank you. Now, the question of the opponent.
So for the pumping speed, you think that it is the amount of volume per second. Is that correct?
Yes.
Yes. So when you increase the straw diameter, the pumping speed decreases. Is that what you're doing?
What do you mean by pumping speed? Do you mean the rotational speed or the
Pumping speed. Because the problem statement talks about the pumping speed.
The pumping speed we adjusted through the drilling press and the
I mean, if you increase the straw diameter, according to experimental results, does the pumping speed increase or not?
The diameter does not have a great impact on distance, but it has an impact on the mass rate and the volume rate out.
So does it have what correlation does it have? Is it bigger diameter meaning more pumping speed or not?
Bigger diameter speed, it depends on the parameters, but generally yes.
But you talked about capillary action. So is there a boundary point?
I think we showed that in the graph where the curve.
Okay, in page 7, what is the definition of the straw height? What is the definition?
Straw height? Oh.
Height of the pump.
Can you go to the next one? Next. Oh.
Okay, this is the straw height.
Yeah.
Okay. Have you ever considered the reverse depth of the straw inside the water?
Yeah, we investigated through the impact of fluids.
So in the page 8, we use velocity here. So have you ever calculated the velocity in your experiment or angular velocity in your experiment?
Angular velocity.
Because I see in your graph that you use voltage. So what does it mean?
Go to the minus side. After thank you, there's the appendix. For the voltage ones, we
Okay.
for clear.
straw. This is the problem statement. I think the most important part of the phenomenon is the pumping speed and other reference parameters and how it affects the pumping speed. However, in their experiment, they only talk about the velocity and voltages of the different straws. So I don't know how to find the correlation between pumping speed from their data. So here is the outline. We have problem statement, and they have many theories to try to explain the phenomenon, including the centrifugal force, Bernoulli's law, and buoyancy. And they have made an experiment setup to find the correlation between theory and experiment. Okay, here's the summary. I think they used the range of water spilled to calculate the velocity. However, they didn't state that clear in their report, so I think that should be clarified later. And they experiment with different voltages, angles, and diameters. And I can't quite understand what they are trying to talk about when they experiment with different voltages, angles, and diameters. I don't know how it affects the pumping speed. They didn't explain that correctly. And they explain the theory of centrifugal force, buoyancy, and Bernoulli equation. Okay, the report has some strengths. It considers different angles, and it considers an unbalanced straw, which maybe we can talk about the precision of the straw while the motor is turning. Also, they have a very clear theory on how the other relevant parameters affect the pumping speed. And they have a lot of areas for improvement, like the lack of having data. The data is insufficient to prove your theory correct. Also, error bars did not show in some of the graphs, which is something they can add. And the definition of pumping speed, they have defined the pumping speed. However, did not put it in your graph to explain. Okay, so here can we begin our discussion. So for the first part, can you turn to page 9?
In the non-inertial frame, yes.
In the non-inertial frame. Yeah. So you think that the Bernoulli's law is negative.
Yeah.
Well, from your theories,
Yeah.
you can find the exit velocity of the water. Yeah.
Yeah.
And how does the exit velocity of the water affect the pumping speed?
Oh, okay. We want to clarify that clearly. So our initial goal was to calculate the initial exit velocity multiplied by the area that the water actually fills in to calculate exactly how much water exits the pump in a second. So that's how it's correlated. And in our further slides, we try to observe how much water exits in the area of the different diameters of the pump and diameters of those in different diameters. And we observe that the thicker the diameter gets, the less water it tends to fill out. So even though the diameter could increase, it doesn't really have an impact on the pumping speed itself. But when it comes to the
So what you're indicating is that when the diameter increases, the exit velocity decreases. Is that what you're talking about?
The exit velocity is the same in different diameters.
So the exit velocity doesn't change.
Yes, in different diameters.
But you just said that the pumping speed is the exit velocity times by the area of the cross-section area of the straw.
That is due to the area that the water actually fills in. So for bigger diameters, like it has a less tendency to fill in the water in the pump.
Do you have the photos to prove your observation?
Can you go to slide over here? So if you see there, it's a bit blurry, but it fills in the water like when at the middle point. But then as it goes up, the water doesn't actually fill in the water in the.
And how do you make sure that this won't be effective while the area changes? How do you make sure?
What do you mean by that?
How do you make sure that the area, cross-section area of this water deep doesn't increase while the
As the revolutions per second increases of the drilling speed, this tends to fill in the water completely. So from that you can observe. But as the revolution speed increases for the bigger diameters, it tends to not fill in the water because the initial velocity is up much faster.
So you have any other or any data points?
Data points?
Because we cannot really measure the pumping speed when you.
The pumping speed, we could calculate by the mass of the water sprayed out, and this is the mass of the water.
So how do you find out the mass of the water sprayed out?
We have it here, the mass of the, so you can.
How
so,
do you do your experiment?
Oh,
You didn't talk about it yourself.
Okay, we'll clarify that here. So we initially calculated the mass of the water in the beaker, and then we placed it through our experimental setup, and then we calculated how much change of the mass of the water occurred, and we divided by the time we actually calculated the setup. So I think
May I use the back book?
I think we clarified that in our initial assumptions.
So what you're measuring is actually the average pumping speed. So when you say you have a container, right? And you put the straw here and it turns.
Yeah.
And the water spills out.
Yeah.
And you calculate how much mass is increased.
Yes.
And through let's say, the volume. And you calculate this, define it as the pumping speed. Is that correct?
Yeah, well, it's the mass, but mass and volume, it's interchangeable in the water context.
So what do you think about, so you think the pumping speed is mass or volume? The definition of pumping speed.
The definition of pumping speed is mass, because we based mass to calculate all the pumping speed in our experimentations, but we believe it's interchangeable as mass and the density of the water is.
So in your graph, why did you use mass pumped out and not pumping speed?
We labeled that in the axis.
Okay, I think the label should be more clear.
Okay, yeah.
And change it to
Okay.
So when you're measuring here, it's actually the average pumping speed since you have the time frame.
Yeah.
So will the pumping speed change throughout the long?
Pumping speed change. In our experimentation, we assume that because the interval we measure is from 10 to 15 seconds, and there's a very low possibility that in this interval, the mass of the water that is pumped out per second will fluctuate. So we just assume that it's an average pumping speed.
I think that we might actually early stages of the experiment. The pumping speed might be something like this. So how do you make sure?
Why do you think it's going to be like this?
Because the pumping speed in the early stages of the experiment is zero, and when you have the omega u. So if we go back to the theory, you said that there will be a centrifugal force, right?
Yeah.
As the centrifugal force.
Yeah, yeah.
And you say that the velocity here is zero when it comes into the straw.
Yeah, initial velocity.
And the exit velocity is that.
Yeah.
So why is this zero? Have you ever considered continuity in your equation?
We assume
Because this velocity should be the same as the exit velocity. Well, the pumping speed is the same. So maybe in the early stages of the experiment, we can assume it this way because the velocity is zero, the initial velocity is zero. But when the pumping process is stable, you need to consider continuity in your equation. So when you're measuring the 10 to 15 second time frame, what are you actually measuring right here?
we're measuring the initial exit velocity here. So we assume that it's going to be like about 10 seconds along this interval. So we just measure the mass of the water sprayed out in this interval.
So you don't take account of continuity.
Oh, like in the further experimentations. No, but if we take, okay, but if we take the continuity into consideration, then the level of water will come down very quickly. So that means like there's going to be a fluctuation in the buoyant force.
Well, it has nothing to do. I don't think it has anything to do with the buoyant force.
Oh, also there will be a significant impact of continuity because for some of this, as the revolutions of speed increases, the water won't fill in the straw completely. So we cannot really assume that we will be.
So you think that as in this is a straw,
Yeah.
the water droplets are actually like this, and they are like little objects moving up.
No. We think it's going to, at the initial stage, it's going to fill in the thing, but then as it goes up, it's going to spill in like that. So it's like,
well, this is a fluid motion. You should have considered continuity.
no, but continuity only applies on this context. No, we can't really measure the area over here.
You can measure the area over here, but you need to consider continuity because velocity here.
Then how would you consider it?
Here.
No, that's a person. But then how would you consider it in your experimentation?
Well, we can't. So we use different experimental methods to measure. Well, I'm talking about group report and not combined.
Okay.
So do you think that this might be the cause of derivation for experiment?
No, we still
So
assume.
you think that your theory is completely correct, and your experiment is wrong. Is that correct?
Experiment, why do you think the experiment is?
So for experimental results, I can't really see the correlation between the experimental results and your theory.
In what part do you not see the correlation? Okay, let me clarify one thing. So when the velocity increases, right, then the exit velocity over here, it increases. However, as the diameter of the thing increases, it's going to shoot out like less area, it's going to fill out less area of water. So even if the velocity increases, rotational speed increases on like the further experiments, the mass of the thing goes.
So how does the voltage motor affect with the angular velocity? Have you ever measured your angular velocity?
Yeah, we measured the angular velocity.
Then why do you use the voltage of motor? Because the voltage of motor doesn't really correlate with the angular velocity due to the buoyancy force that you talked about. So is this graph incorrect?
So we want to clarify one thing.
And I don't think anything, your theory has anything about the voltage motor. So why can you draw a line?
The voltage one. Can you go to the initial like setup where we showed the video? So yeah, over here. Initial. So over here, we used a drill press setup over here for the low, middle, and high revolutions. But in our experiments, we found out that the middle revolutions has a greater impact when it comes to shooting off how much mass of water is raised up per second. So therefore, we used a voltage supplier to control the middle revolutions. So we assume the low revolutions will be like two revolutions.
So what does the voltage correlate with the theory? Why can't you draw a theoretical line with the voltage? Because in your theoretical equations, I can't see where the voltage is.
Oh, the voltage, as the
Turn
voltage.
to the page of the voltage. Yes, in this page.
Oh.
What does this line mean?
Oh, as the voltage of motor increases.
Where in your theory I can't see the.
Yeah, we will try to add that into our further to improve our experience.
So. Yeah, I don't think you should use the voltage of the motor to represent the angular velocity because there might be drag.
Okay.
So I think if you have any way of measuring the angular velocity that using tracker or something like that, then that way you can know that the angular velocity is constant throughout the time.
So you're suggesting to use a tracker to calculate the actual revolution per second?
Yes, the angular velocity.
Oh yeah. So for the 0.7 voltage of motor, we found out that it correlates to 3.9 revolutions per second, and for 11.11 voltage of motor, we calculated that it correlates to 5 revolutions per second.
Well, then what does the theory line mean?
So
if you correlate in that way, I think your theory needs to have units, you know. And the theory's units is radian and not revolutions per second. So how can you make a theory line right here?
What do you suggest about the radians?
Because
the radians of this doesn't correlate to the actual radius of the pulse.
so how do you measure the velocity? Because the
Velocity.
angular velocity, the velocity is actually the angular velocity times by r.
Okay, time is up.
To summarize the report, the opponent has talked a lot about their experiment and has clarified some major points, like how the coming speed is measured. And they use the mass spilling out of the straw per second to measure the pumping speed. However, I think that this only measures the average pumping speed and doesn't account for the pumping speed changes that may happen during the phenomenon. Also, I think the graph of the reporter isn't correct, and the voltage should be adjusted to angular velocity and using units like radian instead of rotation per second. And I don't think they can draw a theory line with voltage right here. And also, the drag of the pumping stroke could affect the angular velocity. make it uneven. So I think they should be
Time is
more.
up, sorry.
Thank you.
I'd like to ask a question about your one-sided Windows company.
First one, okay.
So I'm wondering about how do you define the frictions that you mentioned, like
Oh,
you
really?
stored the one in stored.
What do I think about?
Like can you go to the fourth diagram that you drew maybe the earlier pages? Oh yeah, this one. So how do you define this one?
Oh, we just neglected that in our free body. Like we recognize the fact that there's a force that's shaping out like the frictional force, but we in our initial assumptions we assumed that this is negligible, so we did not put it in our force body diagram.
Okay, so there is any possibility to consider viscosity in your whole total experiment? Okay, so for the opponents, would you think that that friction, like maybe kind of the viscosity will cause the difference of the speed, the speed at water the whole water gets out?
Figure that may consider capillary action, but not viscosity in your experiment.
Observe. So can we go to the Pullman device? So you've got a elevation angle of the show your place, right? Like this. As I told you earlier, the water doesn't just directly come out as the the elevation angle. It goes like that. It goes like this way. So do you think that
Oh,
difference
you
is?
mean the vent over here that is formed?
The water goes like this, and it would differ as the elevation.
That's because of the mass of the water. I think
Yes.
it's.
Yeah. So you put out into your consideration because it will be sit right here. So
But our main question is to find out the mass of the water that exits the water initially, not the trajectory of the water that shoots out. So do you mean the distance?
yes.
Oh, distance. Go to the slide where. Oh, over here, we can actually get the distance of the velocity of the water here, and then that probably is the distance. So we try to track the initial velocity of the water come down using the distance of the.
Okay. So for just for confirmation, so you see, as you states that if the length of the straw increases, so the rates of the water flow rates will decrease. I'm not so clear about your statements. So as the length increases, what the water flow rate is like, the amount of the water flowing out decreases.
You mean the straw length?
Yeah.
We did not discuss that about the straw length in our experimentation. We did not.
Time is up.
Great to honorable judges and fellow contestants. I'm the reviewer of the urban development here. So I'll start with the reported parts. Okay, so we'll get started from their rainfalls. So they investigate the relevant parameters to about the velocity of the pumping speed and to what extent does the distance vary depending on various changes. And okay, let's go on. So I think that the point of it really do well is like they got clear when we were shut down the whole setup, like how do they measure the measurement, the setup is all really clear, and they consider lots of variable during the experiments. But I think just about the opponent raised, I think about the about the charts, we can there will be equivalent for the charts and the connection between it was not really clear. And for the opponent, I think they do go into deep into their the theory of the result. But I think they over focus on the voltage parts, like they over focus on the charts, and they didn't go into further discussion about other parameters. And for the first discussion, the opponent raised about how does the axis velocity affect the pumping speed. And so reporters stated that the diameter changes. It doesn't affect the exit velocity because the water doesn't fill the strokes completely at large diameter. So basically, it's like no correlation. They stated, but the opponent also find that unconvincible because the lack of the database is not large enough. So we suggest that more experiments and data could be showed up in further improvements. And another is the opponent raised that the voltage of the motor doesn't connect with the problem statement. So I think this is for I think it will be better for the transition into so we're discussing about the velocity, so maybe about the rotating speed. So maybe you can change, you can say that the way to change the voltage into the angular, the rotating speed exactly. So it will for better discussion. And that's it. Thanks.
Thank you.
So we will start with our final remarks. So we define the pumping speed as the mass of the water sprayed out in each of the graphs, and we agree that we should have verified in the variable sides. And each of the parameters have different optimal states to maximize mass pumping speed as showcased in our graphs. And the diameter of the straw showed to have some optimal ratio that balances the capillary force and the greater amount of water sprayed out. And continuity is not useful in our theory because we can't find the cross-sectional area of the straw when the water spills out, and we want to stress this part. We tested that the voltage is proportional to angular velocity, and we'll add that graph in our future presentations. And our initial aim was to fine-tune the 4 revolutions as it was observed to have the best mass per second that the water is sprayed out. And we agree with that we should test different viscosity of water to help test the capillary action impacts in our experiment. Thank you.
Thank you. It's time for question. Any questions? Anyone? Do we have to consider the length of the straw and the degree of the straw? Can you? I mean, it's the length of the straw.
Length of the straw?
Yes.
We did not really consider that, but we assume that the smaller the pump is, the more mass of the water is sprays off.
Another question?
Oh, and also the angle.
Yes. Next question.
How do you measure the exit velocity from the stroke. So for three guys, you can answer. If you want to detect the exit velocity from the stroke, how can you make it? For the report?
Detect the exit velocity.
Yes, yes. How do you measure?
We try to get the exit velocity by measuring the distance of the water is sprayed out and track it back by using the angle together. But yeah, that is how we track it.
Yeah, so I agree with the distant one. So it pumps out as a projection of motion. So I think so you can get the distant and get back to the velocity like from the beginning.
I think the problem statement talks about the pumping speed, so the exit velocity doesn't really change, doesn't really affect doesn't really refer to what the problem statement is actually talking about.
Yes.
So have you considered because I think the driving forces start from the rotation speed, right? But in initial, the rotation speed is from the how to control the rotation speed in the beginning. If you will assume the rotation speed is omega, but once you turn on the initial maybe several seconds, the initial speed is omega, but maybe in the 1 or 2 seconds you already have some water speed out. So how to control this?
So in our experimental setup, we first use the drilling press to get the revolutions per second in like a stable like time, and then we use the elevating tool to like get it up, and then we calculate it.
Fine.
So I have a question. So is there any relationship between the voltage of your machine with the angular velocity?
Yeah, the higher the voltage was, it was observed to have a faster revolutions per second.
Okay.
Yeah, and the purpose of that was so in our preliminary experimentations, we found out when it's rotated with 4 revolutions per second, it turned out to have the most massive water spraying out per second. And then we wanted to fine tune like precisely how fast the drilling thing goes. Would it spray out the most water? So we try to use the voltage supplier to get the precise like spinning speed.
Okay. So therefore I can say the angular velocity itself is the function of the voltage, but you don't know the function it is. No? Okay.
We will try to.
Okay.
Okay, please wait. Sorry. First, for the reporting. 9, 7, 6, and 6. We show 9, 9, 8, 8, and 7. Six, 8, 6, 7, and 6.